So with the task 3 completed, we have a model validation to our liking. We're ready to start using the tool to help make predictions about how to design our project, and that's what we mean by the predicting some of the specific cases. Now, one of the things we've been working on in class, this is of course this is in our geometry modeler discovery, was building up this test board and this fixture where we're going to be able to hold the magnets. If you remember, the idea was that we have a plexiglass or equivalent on top, and we have foam board regions. I'm just going to hide these so we can get to what we're trying to build. Within that foam board, we had a number of slots that were available for the anchor magnets. So the idea is that we should be able to embed as many anchor magnets as we want on this grid. And if we hold this panel vertically, so in this case I've got the X direction going this way, so it would look something like this. The idea is that we can continue on with this same sort of planar magnet strategy, and we can have the float magnet injected into the scene on the top surface of any number of these anchor magnets. Some of these might be filled with actual magnets, some of them just might be holes and void. So the magnet would be allowed to move around the space at our choosing. One of the critical tasks here is to determine how far apart these magnets, any two anchor magnets, might be separated and still allow the magnet to fall through. And that's a case that we set up in class and we talked about, and we're going to do that right now as our final goal for task 4 of this project, to be able to determine what the minimum, or I should say the maximum separation might be to still be able to hold a float magnet and have it reach equilibrium without falling through. So one of the things that we did in class was we drew this scenario out. So imagine we've got our two anchor magnets. We're calling them A1 and A2. They are separated at a distance. I've got my axes kind of reversed here. So in our model, I believe we had X pointed up and Y is pointed this way. So that aside, our scenario is basically identical to this, where we want to determine what that distance is from the float magnet to the origin, which is directly laterally between A1 and A2. So we're trying to determine these two numbers. What's the distance? We're going to call this variable d float. In our simulation model, it happens to be the x coordinate of the local coordinate system for the float magnet. And then we have a variable here called pitch. That's going to be the separation distance. So back to our larger model, this pitch is going to represent maybe this spacing here or this spacing here, depending on how we orient the board. So again, the goal is to calculate d float and pitch, and we're going to set that problem up for you now. So I think the best way to do this is going to be probably to copy, instead of the task 3, let's go ahead and make a copy of task 2. It's a little bit closer. It really doesn't matter which one we choose, but I'm just going to go ahead and make this decision to build up the scenario that we just described. So I'm going to copy task 2. I will paste, and of course it chose the right name again. I'll hide this, and let's just summarize. What we need to do right now is basically have two anchor magnets that are in the same plane, so not stacked like we had in task 3. And we want to make it so that the anchor magnets are going to be separated by, let's see, the value that we wanted to determine was pitch. We're going to call that pitch, the distance between the two magnets. So what I'm going to try is, let's go ahead and duplicate this magnet. So let's go. I've got the global system chosen right now. We have an anchor 1 coordinate system, but I think what we want to do now is let's go ahead and make an anchor 2 coordinate system. So if I want it to be referenced to the global, not to the anchor 1. So the way to do that would be to choose global first. And again, all I'm doing is creating a new coordinate system on top of the one that you're looking at. So I'll zoom in a little bit here. And I'm going to choose this offset origin, and it just wants me to choose the point. And right as soon as I get there and that little sphere shows up, then I know I have it. So let's rename this right away so we don't get confused. We're going to call this anchor 2 CS. So I'll remove, type over this. So now, even though they are in the exact same location right now, it's important that we have them as separate entities. So now what I'll do is I can create something called a parameter. So if you notice, when I click on anchor 1 CS, the origin happens to be the global origin, all zeros. Same thing with anchor 2 CS, okay? All zeros. The reason the float coordinate system is at a different height is because we told it to. So it's got 22.4 right now is the setting. So let's go ahead and use that same idea, but what we're going to do now is determine these, we're going to define these in terms of variables. So imagine if I had a variable that I could use in the y direction. So if I can define a variable and I can make it so that I can make it, change the numerical value of that variable to anything I want, and it would control the separation between anchor 1 and anchor 2 CS. So here's one way to do that. I'm going to just choose one of these, and in the origin, I want anchor 1 to be moved over on the left-hand side some amount, and I want anchor 2 to be moved over on the right hand. And we'll keep them equal in distance, but opposite in direction. So let's start by choosing anchor 1 CS, and I will come in negative, it's the y direction. I want it to be a positive y direction. And let's call this, I'm gonna use capital P and then ITCH was the term that I used. But if you watch this, I'm not done. That's the variable that I want to use, but I'm going to divide it by 2. And then what happens when I hit enter is that the software recognizes that this thing pitch is not a number. It must be a variable. And I'm going to choose the unit type. I believe I'm going to find maybe distance down here. If I can, or maybe it's a length. Let's see. Yeah, there's length. And I know I want it to be in millimeters. I'm working in millimeters. What do I want the value to be? I can just kind of make up a value at the moment. And let's just make sure that it's at least 1 radius, to the left in this example. So that would be 7.5 millimeters. Actually, remember this is pitch divided by 2. So let's go ahead and use the diameter. If I say 15 and I say OK, then it actually moved pitch divided by 2. And that makes sense because the value that is being reported back to me, this is the evaluated value, is actually 7.5. I'm just trying to expand this window so we can see it, but maybe that's as good as I'm. There we go. So pitch divided by 2 is apparently equal to 7.5. So we know we did that right. So now what I want to do is I want to replicate that. So for anchor C1, I want anchor C2 to look just like this with the opposite direction in Y. So if I click on anchor C2, what I can do now is use the same. The variable is already defined, but I want to go in the negative direction. So I'll say negative pitch divided by 2. And all that's happened is a coordinate system has moved. I don't have an object on top of it yet. So if you watch how I've got anchor 2 as my working coordinate, that means that any geometry that I put in the scene now is going to snap to coordinate 2 immediately. So one way to do this, hopefully this would work, is that I'm just going to select anchor 1. I'm going to right click, and if I go to edit and choose copy, and now in the dead space over here, I'm going to right click, and I'm going to go to edit, and I'm going to choose paste. And this all worked out. It appears that I've got my new anchor. I've got my new anchor 2. It actually gave it the appropriate name. It looks like it's assigned. It's connected to that coordinate system. I can see anchor 2 CS. The distance looks correct. So now, if I if I want to change the distance, I'll show you in a second. I'm going to be able to separate these just by changing the value of pitch, and I'll show you how to do that in a second. We're almost done. What I'd like to do is we're almost done setting up the parameters. I want to do the same thing for the float magnet, and if you remember, if I click on float, I don't see anything for the move command because this is also connected to a coordinate system. So if I click on this coordinate system, there it is, and here's the value that we gave it. We're going to call this, I'm just going to say, let's just call it dfloat, capital D F L O A T. It asks us, do we want to create a new variable? And we're going to say same thing. This is going to be a length. So I've gone too far, it looks like. So here's length. We're in millimeters, and let's just make it. We're not going to make it the same as before, but let's go ahead and just say 15 millimeters to kind of keep it out of the way. So so we have the parameters defined. This is exactly the way that we're going to design the board. They're in the appropriate plane. Again, the bottom surface of the float is in the exact same plane as the top surface of the anchor magnets. And now, notice. I want you to notice when I highlight task 4, I'll see here are these two variables. In properties, these variables that we just created are available for us. And now we get to change them at will. So if I change the pitch to 20, you just saw that they separated out. And the same thing with the float. If I change the float to 25, it's also going to separate out. So now we are at the beginning stage of setting up a parametric analysis where parametric basically means we get to assign various values to these variables and look at the result. So we're going to work on setting that up in a second. So that's what we're going to work on next. Now this is where parametric analysis comes in. We've done some forms of this in class before in probably haphazard fashion. What I'd like to do now is set up what's called an optometrics run. This is just a different way of saying we want to build up a parametric run, for at least for us right now. So what I want you to do is to right click on optometrics, and I want you to go to the add menu, and we're gonna go to a parametric. We're gonna choose parametric. When we do that, just if you follow these steps, we're gonna add a couple of variables, and we're going to add values. So let's go ahead and say let's add first. I want to add. We get to choose. We only have two variables available, right? So let's go ahead and start with pitch, and you can just read these out. We have a nominal value. That's what I typed in right before we went to the parametric form. But then we have these different values that we can also evaluate. So if you remember, pitch had to be at least I believe 15 millimeters for it to make sense. If the pitch was if the pitch is smaller than 15 millimeters, the magnets will be fused together. They'll be overlapping each other, and that's non-physical, right? So we have to just remember that that's a lower limit is 15, and 30 seems as good as any for a high value for now. We can come back and edit this later, and I'll probably have you do that. Let's go ahead and say 5 millimeter steps. So if you've got it filled out like this, I'm going to add, and I'm going to go ahead and do some float variables as well. So if I go to dfloat, I'm going to choose, if you remember, I think we're at 20 millimeters maybe for the float position right now. So this is the height of the magnet. I'm going to just go with positions of, let's say, 10 millimeters to, let's say, 20 millimeters. And I'll do 5 increments there, 5 millimeter increments. Okay. So when I do that, I just went pretty fast there. I'll go back to here. You can pitch. You can grab any one of these variables and edit and verify what you've seen. Make sure that you add it to this section. I'm going to cancel because I've already done it. Same thing goes with this. You can always go back and edit and verify that you see the values. The last verification that I like to do is I go to Table, and look at how these are going to play off of each other. So I'm going to run 12 simulations in this example that have all these variables mixed. They're permeated with each other, right? So I'm going to go through all the permutations here. And this is really just an introduction to how parametric analysis works. I still give you the assignment of determining what those values are to meet equilibrium. And I don't know if we're going to get lucky and one of those values that we run is going to be it. That's going to be for you to decide. So the last thing I wanted to show you is that if to verify that everything makes sense, a good habit is to come and do a quick animation. So if I go to Optometrics, parametric setup 1 is what I have now. I'm going to go to animate, and just go ahead and choose the default that comes up there. I can see all the things that it wants to go through, and let's see if this makes sense. Is this a physically obtainable object? A parametric run, right? So you can see the parameters are just kind of stepping through. This makes sense. The float, it's legal for the float to be, it's not intersecting because they're in separate planes, so it comes on top of the two. That's fair. The two anchor magnets are not interfering with each other. So all of these configurations are possible. We can physically create these conditions. So I like this. I'm going to go ahead and stop this animation. That was just a verification. So I'm going to do a quick validation. Looks like we're okay there. There is one thing I forgot to check, and it's notice that we did not apply the force on both anchors like we had been doing. So let's correct that. You should know how to do this by now. I'm going to choose both anchors, and now I'm going to right click, and I'm going to say reassign. So now that's fixed, and now I'm going to go to mesh, and if I just verify real quick that if I select the assignment, sure enough, my anchor is missing. I want all three of these to be in the same mesh assignment. So I selected them all, and I right-click on length 1, and now I'm going to say reassign. Final verification is to make sure I didn't miss anything, and I just say select assignment, and they're all there. Now I've got everything I need. I'm going to validate these results. That looks good, and I'm going to close this out. And I'm going to start the analysis while I remind you of what your task is. You're about to run through all these different cases. This is going to take longer than all the other ones because I believe we have 12 total cases. And we will review how to access those results. They're going to be on the form, on the built-in results. They should already be linked into that table. You might have to play around with how to find all the different parametric cases, but I believe that's going to be straightforward for you. We'll talk about it in class. Reminder for you is that your challenge is to get these values. And I don't know these values. I just plug a couple of parametric choices into the simulation, and we would have to be very lucky to find the condition where we chose defloat and pitch so that we reach the equilibrium condition. So remember, what we're looking for is that the force that we measure between, in the x direction on the float magnet is going to be equal and opposite to the force in the x direction of both anchor magnets. And we know what that number is. It's been 32 millinewtons. Of course, our solution has been under predicting, so we expect it to be a little bit closer to 30 millinewtons, I believe. So that's the challenge for you, is to look at your parametric results as you get them, and you have to make decisions on how to redefine those parameters and the spacing and determine what these values are going to be. And your verification is that you're gonna end up with one configuration of a pitch with the float, with the defloat, that's gonna give you that 32 millinewtons in the x direction. So good luck. That's the end of Task 4, and we'll be talking certainly more about this in class.